Okay, so today what we want to do is we want to find limits without a graph and without a table. How can we do it? All right. And so these are some properties that we're going to use for limits that's going to allow us to do that. Okay. So first off, these letters that you see, capital L, capital M, little c, and lowercase k are all real numbers. Okay. So those are numbers that we're used to, not imaginary numbers, real numbers. Okay. So the very first property is this. If we find the limit as x approaches c of some constant k, then that just has to be k, because this isn't changing. So if x isn't changing, or if x is getting closer and closer to c, but this y value is a number, it's just going to stay the same. Okay, so an example of this would be something like this. The limit as x approaches 3 of 7. Well, x is getting closer to 3, but the function's still 7, right? It's staying 7. It's always 7. So therefore, this is going to equal 7. Okay? How about the limit as x approaches c of x? Well, if x is getting closer to c, then this would also have to be getting closer and closer to c. So an example of this would be the limit as x approaches 3 of x. And then that would have to be, well, if x is getting closer to 3, then the output would have to be getting closer and closer to 3 also, okay? And then we come to this direct substitution, okay? And this works if f is continuous. In other words, there's no breaks in it, okay? And we're going to talk about more about breaks in a graph and what causes breaks in a graph. You already know some, like an asymptote, okay, or a hole, okay? Those are all breaks in a graph, okay? So if we take the limit as x approaches c of f of x, and there's not a break at c, then all we have to do is plug c in. That's all we have to do, okay? So that's a main one. That is the go-to thing, okay? All right, and then if we can't do this direct substitution, then there's going to be other techniques that I show you over the next couple days, okay? So here's one. The limit as x approaches c of f of x is equal to L. Okay, so I'm making this statement, okay? As x is getting closer and closer to c, the function is getting closer and closer to L. That's what this is telling us. It's not saying that f of c is L. It's just telling us that as x gets closer to c, the function gets closer to L. And for this one, as x approaches c, g of x is getting closer and closer to some number m, okay? So this next one, I'm going to slide it up a little bit. Okay, so this next rule is that it's called the sum rule. If we take the limit of two functions that we're adding together, all we have to do is take the limit of the first function plus the limit of the second function, and it will just come out to be L plus M. Pretty easy, okay? The difference rule is same idea, but it's going to be a difference instead of a sum. And if we take the limit as x approaches c of two functions that we're subtracting, we can do it individually. And then this would be L minus M. Product rule, same idea. Okay, the limit as x approaches c of f of x times, because remember that dot, closed dot means times, g of x. Then all we need to do with that is take the limit as x approaches c of f of x and multiply that by the limit as x approaches c of g of x, and then we wind up with L times M, okay? Constant multiple rule. If we take the limit as x approaches c, now k is going to be some number like 5 or something like that, okay? K times f of x, then that would be equivalent as k times the limit as x approaches c of f of x, okay? So this would be k, that's the k right there. This limit from right here is L, okay? So an example of this would be something like this. If we found the limit as x approaches 3 of 5 times f of x, we could figure that out by just taking 5 and multiplying it by the limit as x approaches 3 of f of x, okay? Now, the quotient rule, okay, almost identical as the product rule, except for one thing, okay? So if we take the limit as x approaches c of f of x over g of x, that's equivalent to taking the limit of the numerator over the same limit of the denominator, okay? And that would be, because this one is L, right, from up here, this numerator is L, okay? And the denominator is going to wind up being M. Now, there's one time that this doesn't work, and we're going to have to figure out other things, and that's the next day's lesson, okay? That's tomorrow's lesson, is what if this M comes out to be 0, okay? And we'll talk about that tomorrow. It's not going to happen today, okay? And then the power rule, if we take the limit as x approaches c of f of x raised to this power r over s, okay, then what we can do is we can do the limit of the function and just raise it to the power. So it'd be L raised to the R over S. Okay, now for probably the hardest one to understand. I'm going to slide it up just a little bit. It's called the composition function rule, okay? Okay, so for this next one, if we take the limit as x approaches c of f of g of x. Now remember, from this is right at the end, right before we went out on distance learning, okay? This is putting, okay, we put x into g. Now that's a y, but now that y becomes the x that we're putting into the function, okay? All right, so to figure this one out, okay, and remember, all of these are the one-sided limits from either side have to exist, okay? That's gonna be really important, okay? So the limit as x approaches c of f of g of x, okay? That's equivalent to taking the function of the limit as x approaches c of g of x. Now, what we know is that the limit as x approaches c of g of x, okay, this is getting closer and closer and closer to the number. And you know what? This is a typo I just caught, okay? This is getting closer and close. Oh, I take that back. No, hold on. My mistake. This isn't a typo. Okay, so let me back up. Sorry. Okay, if we take the limit as x approaches c of f of g of x, okay, what we can do is here's our x, okay, and we can take the limit as x approaches c of g of x, okay. So what is this telling us? X is getting closer to c. When x does that, g of x from up here gets closer and closer to m, right? And this is m, and that is the output for this, right? It's the output for g, but that means this output for g becomes the input for f. So it winds up being that x is getting closer and closer to m for this function f of x, okay? You're not going to have this really tonight, okay? You're going to have it. So I'm just kind of, this is an intro today, all right? And we'll deal with this more. I'll give you specific problems where we have to figure this out. And we're going to use limits that are from graphs, okay, to figure this out sometimes. Okay, so those are the properties. Now I'm going to go and do some problems and show you how we use these, okay? Okay, so for this first example, all right, I'm going to work it all the way through. I'm going to show all the work of why this is true, okay? So, and then say, hey, look, we could have done this, all right? So this is going to be the long way at first, okay? So if we want to find the limit as x approaches c of x cubed plus 4x squared, that's a function plus another function minus this constant, right? So what we could do is we could do the limit as x approaches the c of x cubed plus, okay, the limit as x approaches c of 4x squared, and then minus the limit as x approaches c of 3, the number 3. Okay, now what allowed me to do that? I used the sum and difference rules, okay? Because this is the sum and this is the difference, all right? So I just added and subtracted because that's what you can do with sum and difference rules. Okay, now right here, this is the power rule, okay? So then that means we could take the limit as x approaches c of x and raise it to the third power. So that would look like this. The limit as x approaches c of x raised to the third power. Plus, okay, so this is a constant that's 4 times a function, right? So we can use the constant multiple rule, and we can take the 4 and multiply that by the limit as x approaches c of x squared, okay? And then minus, this one's actually ready to go, okay? Now I'm gonna keep writing this and I'm gonna do them all at once, but really this is the limit of a constant rule, okay? So minus the limit as x approaches c of 3, okay? This one we're ready to go, this one we're not, okay? So we can do one more step here, okay? So this is equal to the limit as x approaches c of x raised to the third power plus 4 times, okay, so this is the limit as x approaches c of x squared. That's the power rule. So that says I can take the limit as x approaches c of x and just simply raise that to the second power, and then minus the limit as x approaches c of 3. Well, what do we know about the limit as x approaches c of x? Well, if x is approaching c, this has to approach c, right? So this winds up being c to the third power. And then plus 4 times, and look what this happens, okay? Limit as x approaches c of x. Well, if x approaches c of x, if x is approaching c, this x has to be approaching c, so it's going to be c squared. So this is 4c squared. And minus the limit as x approaches c of this constant. Well, as x approaches c, this is always staying 3, right? It's always staying 3. So that means this is just going to be minus the constant 3. Okay, now look what we could have done. All right, now this is all the work. This is the justification of why this is true. And this is the last time we'll do it, okay, because this is kind of a pain. But look what we could have done. We could have just taken the c and plugged it in here. That would be c cubed. We could have taken the c and plugged it in here. That would be 4c squared. See what happens? And then minus 3. So that's what we're going to do. That's called direct substitution. So this is all leading up to us just allowing us to put c in, okay? All right, unless there's problems, and we're not going to really have that today unless there's some problems that we might see, okay? Okay, so for this one, okay, is there any problems? And the problems are going to happen for the denominator here, okay? Is there any problems with putting c in here directly? No, that'd be c squared plus 5. That doesn't cause this to be 0. If it causes it to be 0, that we'd have problems, okay? But we're not, right? So what does this tell us we could do? We can just plug this in, okay? So this winds up being simply, well, everywhere we see x, we're going to do a direct substitution with c. So that'd be c to the 4th plus c squared minus 1 all over c squared plus 5. And we're done. That's it. That's the direct substitution. Okay? That's all there is to it. Okay? Now, if there's problems when the denominator is 0 and other things, okay? We're going to deal with that tomorrow. And I should have said this too. When we come into problems, you'll see when we come into problems, okay? When the problems happen, you'll see like, oh yeah, I remember we can't do that, okay? So you're going to see that you won't see that today, okay? So if we want to take the limit as x approaches 3 of x squared times 2 minus x, what I always want you to try to do is just try to do a direct substitution. That's the first go-to, and see if there's any problems with doing that. If there is, that's when we have to figure out another way to do it, okay? So what does this mean? Everywhere we see x, we replace it with 3. So this would be equal to 3 squared times 2 minus 3, close the parenthesis, close the bracket, okay? Now, this would be, in parentheses here, this would be 2 minus 3, so this would be 3 squared times negative 1. 3 squared is 9, and then 9 times negative 1 would be negative 9, so that'd be negative 9. And see, there's no problems. It comes out to be negative 9. No problems, okay? Okay, so for this next one, we want to find the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. Okay, so we want to try to do direct substitution. If we plug a 1 in here, that would be 1 squared plus 1 plus 2 over 1 plus 1. Okay, so 1 squared would be 1, plus 1 is 2, plus another 2 is 4. So this would be 4 over 1 plus 1, which is 2. And 4 divided by 2 is 2. There's your answer. The limit as x approaches 1 of this function is 2. Now, there would be problems if x was approaching negative 1, okay? Because if x was approaching negative 1, that's going to cause this denominator to be 0. That's where the problems are going to happen. They're not going to happen today, okay? All right, how about this one, okay? Let's go to the next one. Okay, So the limit as x approaches 0 of sine of x. So that would be sine of angle 0. Okay, so this is a trig function. So I'm going to draw my diagram. I know my angle is 0, so that means I'm right here on the positive x-axis, okay, because my angle is 0. Okay, and when that happens, when I land on one of these quadrants, remember, I'm going to make my r be 1. If my radius of that circle is 1, that means the coordinates of this point would have to be, the x would have to be 1, because the x and the radius would have to be the same. Okay, so 1, and because I'm going right, that's a positive 1. My y, I didn't go up and down at all, so my y is 0. Okay, remember sine is y over your r. So this would be 0 over 1. So then that would equal 0. Okay, so this is why I went over evaluating trig functions with you guys. Okay, let's go to the next problem. Okay, I want to find the limit as x approaches 7 pi over 6 of cosine x. Well, let's try the direct substitution. Okay, so what's cosine of 7 pi over 6? Okay, so we got to draw a diagram for this, right? Because it's a trig function again. Okay, so I know right here, if I start right here at 0, this would be 6 pi over 6. And you guys, I'm going to keep, I know some of you have got this, and I'm proud of you for getting it, but I'm just going to keep going over this diagram until you guys get it, okay? So right here, 6 pi over 6, we actually want 7 pi over 6, so we need to go one more pi over 6. Okay, so this rotation would be 7 pi over 6. This extra angle we had to go is called the reference angle, and that's pi over 6. This angle would be pi over 3. This is a right angle. Always, 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 the side that's opposite the pi over 6 would be 1. And because I'm going down, it's going to be a negative 1. And the side that's opposite pi over 3 is the square root of 3, but I'm going to go left, right? I'm going left and down. Down is negative, also left is negative. So this would be negative square root of 3. And then this would be 2, okay? Now, cosine is my x over my r. This negative square root of 3 is my x, and my r is 2. So this would be equivalent to negative square root of 3 over 2, okay? And that's the limit to this, okay? Now, if you tried to do this with like a table, you wouldn't get the exact value. You would get an approximation, but this is the exact value of this limit. It's getting closer and closer to the number negative square root of 3 over 2, okay? All right, let's go to the next problem. Okay, for this next problem, we want to take the limit as x approaches 1 of 2 plus natural log of x. Remember, ln of x is natural log of x. Okay, so that would mean, let's try to do the direct substitution. So that means this would be 2 plus ln of 1, because we're putting 1 in for the x, right? Direct substitution, okay? Now, how do you figure out natural logs? Okay, we haven't done this in a while, okay? Remember, natural log undoes e. So we can actually find the exact value of this if we can rewrite 1 as e to a power, and we can, all right? Because a number raised to the 0 power is 1. So this would be 2 plus ln of e to the 0. Okay, now remember this natural log, the base is e. And so it's natural log of e to the 0, right? These are going to undo each other, and you're going to be left with 0. Okay, so this is equal to 2 plus 0, because this becomes 0, and that's equal to 2. Okay, and that's how you do direct substitution. I did some trig functions. I did the natural logarithm function with you. Okay, remember the natural log of e to the x is equal to x, and also e to the ln of x is equal to x. Remember, they undo each other. Natural log undoes e to the x, and e raised to the natural log, they undo each other. Okay, so that's just something that's something that I used right here. I rewrote the 1 as e to the 0 so that these would undo each other, and we'd be left with that 0 right there. Okay, all right, you guys, let's go to the next problem. Okay, so this is properties that forces you to do This forces you to use the properties, okay? So we know from this that the limit as x approaches c of f of x is equal to 3. So as x gets closer and closer to c, f of x is getting closer and closer to the number 3. And for this one, as x is getting closer and closer to the number c, okay, g of x is getting closer and closer to 8. So we know that this limit exists. That means, okay, that the one-sided limits as x approaches c from the left and the limit as x approaches c from the right of f of x both are 3. For this to exist, the one-sided limits exist, okay? Same thing with this one, okay? To say that the limit as x approaches c of g of x is equal to 8 means that as you approach c from the left and from the right, both of those limits are also 8, okay? And then we have this function h of x is equal to x squared, okay? So here we go. Let's do some problems, okay? Find the limit as x approaches c of 3 f of x, okay? So whenever you have a constant times a function, you could bring that 3 out. So this is equivalent to 3 times the limit as x approaches c of f of x. Okay, now we know that this one from up here, this is 3. So this is equal to 3 times 3. And 3 times 3 is 9. Okay, that's all you have to do for that one. I'm going to slide this up a little bit. Okay, I'm going to come back and refer to this. I'm going to keep referring to this. Okay, so the limit as x approaches c of f of x times g of x, that's equivalent to the limit as x approaches c of f of x times the limit as x approaches c of g of x. I'm going to zoom out just a little bit so we can go back and look at that top. Okay, so right here, this limit as x approaches c of f of x. Well, we know from up here that f of x is getting closer and closer to 3. So this one's equal to 3, and then we have the multiplication there. And then this one, as x is getting closer and closer to c, g of x, this is telling us g of x is getting closer and closer to 8. So this would be 3 times 8, and 3 times 8 is 24. Okay, so the next one is the composition one, okay? So I'm going to slide up just a little bit, okay? Now to figure this out, okay, this is my x, okay, and g of x is the output, but we're taking that output and it becomes the input for h, okay? So to do this, we would have to do this. This would be h, okay, of the limit as x approaches c of g of x. Okay, now what we know is that, and this is important, as x gets closer and closer to c, we know g of x is getting, let me slide it up a little bit, g of x is getting closer and closer to 8. It doesn't mean it is 8, it means it's getting closer and closer to 8, okay? So this inside, okay, g of x is getting closer and closer to 8, which means this is getting closer and closer to 8, okay? So that becomes, and this is the hard part for this, and I know this is hard, okay? And hopefully I'm making this easy, but I know it's hard, okay? As x approaches c of g of x is getting closer and closer to 8. That becomes my x for h, and this is getting closer and closer and closer to 8. So my input for h is getting closer and closer to 8. So this becomes the limit as x gets closer and closer to 8 of h of x. Okay? X is getting closer to c, but as x gets closer to c, g of x is getting closer to 8. That means the input for h, which is an x, is getting closer and closer to 8. And that's why I switch this to x is approaching 8. So whatever this is, whatever g of x is, the inside function is getting closer and closer to, that becomes your x is going to get closer and closer to that value, okay? Hopefully, maybe if I explain it that way, it helps, okay? Now, what do we know from up above, okay? h of x is x squared, right? From up here, h of x is equal to x squared. Can I do a direct substitution? Yeah. Okay, so what this means is that if I do a direct substitution here, that means this becomes 8 squared, which is 64. So this limit is 64. Okay, it's as x approaches c, this function, this composition gets closer and closer to 64. Okay. All right, that was a lot. Okay, but hopefully we went kind of fast. Direct substitution is the go-to thing. We try that first, and then if it doesn't work, then we come up with other ways. And basically the rest of the unit is coming up with the other ways. All right, guys, that's it.